Can you see the screen, the slides?
Yes.
So in the last couple of lectures, we had been discussing about principal component analysis and some other applications of SVD, say for example, the low rank approximation and so on. So today we will move back to singular value decomposition and study some of their properties. So as we had discussed earlier, like whenever we have any matrix, even if it is not square, even if it is not invertible and so on, a singular value decomposition can always be defined. So consider any m cross n matrix where m need not be equal to n. So we write it in this form: A is equal to U sigma V transpose, where U, as we know, is an orthonormal matrix where its different columns are the left singular vectors of A. This V is another orthonormal matrix whose columns are the right singular vectors of A, and this sigma is a diagonal matrix which like whose non-zero diagonal entries are these are basically the singular values of A, and they are from top to bottom, they are arranged as or they are numbered as the first singular value sigma 1, the second singular value sigma 2, etc. And we also know that sigma 1 is greater than equal to sigma 2, which is greater than equal to sigma 3, etc. And the number of non-zero singular values is equal to R, where R is the rank of the matrix. There can be further singular values, but they will be zero. I mean, the number of the way singular values were defined, there can be n of them, where n is the number of columns of the matrix. But if the rank of the matrix R is less than n, then the remaining singular values, that is sigma of R plus 1, R plus 2, all the way up to sigma n, they are going to be 0. So the number of non-zero singular values is equal to the rank of the matrix. Now we are going to define something called the 2 norm of the matrix. Now for a vector, in case of a vector, we know what is the L1 norm, L2 norm, etc. In case of matrix, we have so far dealt with what is known as the Frobenius norm. Now Frobenius norm of a matrix is effectively same as the L2 norm of a vector. That is, we take the squares of all the entries, add them up, and then take the square root. That's if it is done on a vector, that's called the L2 norm. If it is done on a matrix, it's called the Frobenius norm. Now a matrix also has other kinds of norms defined on it. The most well-known kind of norm on the matrix, this is sometimes also known as the operator norm, and sometimes it's called the 2 norm also. So the 2 norm or the operator norm of the matrix denoted like this. So if this were a vector, then this notation with the 2 written as the subscript, this would have indicated the L2 norm. But in case of a matrix, it denotes the 2 norm or the operator norm, which is defined in this way. That is, for all vectors x, for the maximum possible value of this quantity, which is the L2 norm of Ax divided by the L2 norm of x. So since remember that A is a m cross n matrix, right? And X is a n dimensional vector. So Ax, this has to be an m cross n cross n cross 1. That is, basically Ax has to be an m cross 1 vector. So since it is a vector, it will have its L2 norm. So I can, that's what I am computing. And below in the denominator also, X, as we had seen, is an n cross 1 matrix. So that will also have its L2 norm. So on top in the numerator, we are basically calculating the L2 norm of a m cross n, m dimensional vector. And in the denominator, we are computing the L2 norm of a n dimensional vector. Okay. And so this like this kind of quantity can be computed for all x, which all vectors x which is n dimensional, except x equal to 0, that is the 0 vector. So among all the non-zero x vectors, that the maximum value of this particular quantity, that is called the that is called the 2 norm or the operator norm of the matrix A. So this can also be written, this what we have written here can as well be written in a slightly different way. That is, among all the vectors x, I mean n dimensional vectors x, whose L2 norm is 1, I mean the unit vectors, the n among all n dimensional unit vectors, the maximum possible value of ax. Okay, I mean the ax L2 norm. So this is the definition of the operator norm or the 2 norm of the matrix. Now we are going to see how to compute the operator norm of the matrix using the concept of SVD. So let us consider so let us we already know that that U is basically the set of unitary vectors. I mean the columns of U are unitary vectors which are all orthogonal to each other. So so basically they define a basis for the space Rm, and similarly V, there are n of them, and so they are n dimensional orthogonal or orthonormal vectors which define a basis for Rn. Okay? And also we also remember this relation. Okay, A into V1 is equal to sigma 1 into U1. Why? Because this is precisely the way the we had defined U1. So remember that we had started off with the definition of V1 and sigma 1, and U1 had followed from that. So this is like this is this relation holds by definition. I mean, so we know that AV1 is equal to sigma 1 U1, AV2 equal to sigma 2 V2, AV3 is equal to sigma 3 U3, etc., etc. So now when we are talking about the L2 norm, so like as already discussed, this is equal to the maximum value of this norm divided by this norm. Now since this is the maximum possible value, so if we take any arbitrary n dimensional vector, let us say V1, so V1 being the first right singular value of this thing of A. So now if instead of x, if I take replace a, so these like I can compute this for all possible values of x. Now suppose if I choose x equal to V1. Now so basically, so this is the quantity which I get. Now this quantity has to be less than or equal to the 2 norm. Why? Because the 2 norm is the maximum possible value of this quantity which is achieved for some x which we don't know as yet which x. But if it is any arbitrary x such as V1, the value can be less than equal to the operator norm only. It cannot be greater than that because this is a maximum already. But now if you consider the denominator, so we know that these vectors, they are unitary, right? So which means that their L2 norm is equal to 1. So the denominator here immediately becomes equal to 1. Now if you consider the numerator, so this is AV1, but we know that AV1 is equal to sigma 1 U1. So taking the L2 norm of AV1 is the same as taking the L2 norm of sigma 1 U1. But what is the L2 norm of sigma 1 U1? So we know that U1 is again an unitary vector, and sigma 1 is some number constant. So I can write it as well. The sigma 1 I can bring out as common, and I am left with just the L2 norm of U1, which is nothing but 1, because just like V1 is an unitary vector, similarly U1 is also an unitary vector. So we are left with sigma 1. What is sigma 1? Sigma 1 is the first singular value of A. So from this we can see what follows here is that the 2 norm of the matrix is greater than equal to the first singular value, which is sigma, or the largest singular value, which is sigma 1. Okay, so this is the first relation. Remember this relation, which is just saying that the 2 norm or the operator norm of the matrix is greater than or equal to its first singular value. Now let us consider any vector x which is n-dimensional. Why n-dimensional? Because here we are talking about the x vector which we are talking about here has got to be n-dimensional, right? Because we have to multiply it against I have to multiply it with m cross n matrix. So this x has to be n-dimensional. Now remember that remember that if we consider these V matrix, the columns of V are basically the singular right singular vectors of the matrix A. But what is the size of V? So we will remember that V is actually an n cross n matrix. That is, there are n columns V1, V2 up to Vn. Each of them is an n-dimensional vector, and they are orthogonal to each other also. That means what? That means these like this we have discussed much earlier also. That means the columns of V are basically, they are linearly independent and they are n-dimensional and there are n of them. That means what? That means they define a basis for the space Rn, which in turn means that if you consider any vector x which is n-dimensional, which is a part of the Rn space, that vector can be represented as somewhat in this way. That is, it can be considered as a linear combination of the basis vectors which are v1, v2 up to vn. Right? This just follows from definition. Because v1, v2, v3 up to vn, since these are linearly since these n vectors, since they form a basis for Rn, so that means every vector in the Rn space can be represented in this way as a linear combination of the basis vectors. So now if I want to take the L2 norm of x, right, since this is a vector, I can take its L2 norm, which and its squared L2 norm, as we know, is nothing but the dot product of x with itself, or rather x transpose x. And so like you can quite easily work out that so that basically means taking a dot product of this entire thing, this summation, with itself. Now it is easy to understand that this will, like if you consider this like this, C1 V1 plus C2 V2 all the way up to Cn Vn. I am transpose the same thing, C1 V1 plus C2 V2 all the way up to Cn Vn. Right, so now we can of course this basically means that every term here in this summation will have to be multiplied by every term in this summation. So we will basically get these kinds of things. I will get C1 square V1 transpose V1. Right, when I am multiplying this with this, this is what I will get. Similarly, when I am multiplying this with this, what I will get is C2 square V2 transpose V2, etc, etc. And finally I will get when I am multiplying this with this, I will get Cn square Vn transpose Vn. Okay, so these we will get. Along with it, we will also get terms like C1 C2 V1 transpose V2 plus maybe C1 C3 V1 transpose V3, etc, etc. Similarly, we will get C2 C3 V2 transpose V3 and all kinds of cross terms. Okay. So now, based on this, can you give me a simplified expression for what I have written here? What is the simplest way in which we can express this whole expression after any simplification possible?
C1 square C2 square dot Cn.
Right. So so how could you say that? The answer is of course, right? So these are all of these are equal to 0 because they are orthogonal to each other. And similarly, what about these terms? These terms are all
One.
equal to 1 because v1, v2, they are all unitary vectors. That is what we had assumed. So, so this thing, the L2 norm of any vector x is nothing but c1 square plus c2 square, etc. Right? Now, so this in fact should be hardly surprising. That is, we know that the L2 that is, if you consider any n-dimensional vector x, so its L2 squared L2 norm is nothing but the sum of squares of its entries, right? Like x1 square plus x2 square plus up to x plus xn square. But here I am saying that these are also equal to c1 square plus c2 square plus cn square, right? So that's because like I can write this x either like as a linear combination of the like of the standard basis, or I can write it as a linear combination of these bases. So yesterday in the PCA, when discussing about PCA, we had already discussed how a vector can be decomposed in terms of its standard basis. So when I am saying that the L2 norm is equal to the squares of the of its elements, and it is basically this same logic which is at work. The only difference is that in that case, I am writing the vector x as the or I'm decomposing it in terms of the standard basis here, as opposed to this particular basis defined by v1, v2, vn, etc. Now coming back to ax. So ax, so like because here we are talking about on the numerator we are talking about ax. So if I am writing ax, so ax becomes like a times this whole thing c1 v1 plus c2 v2 etc. up to cn vn. Now like here I actually can bring the because this c1, this is a scalar, I can keep the c1 out and just multiply a with v1. So by the property of by distributive and associative property, I can write it as c1 times a of v1 plus c2 times a into a of v2, finally cn times a of vn. Okay, this is straightforward. But what is a v1 equal to? As we know, a v1 is equal to sigma 1 u1, right? That follows from the first definition. So here this expression I can write it as c1 into sigma 1 u1 plus c2 into sigma 2 u2, etc. all the way up to sigma r cr sigma r ur. Why? Because after that, beyond r, I mean for sigma r plus 1, sigma r plus 2 also I can write it all the way up to sigma n vn. But we know that the singular values are non-zero till sigma r, where r is the rank of the matrix. Sigma r plus 1, sigma r plus 2 up to sigma n, they are 0. So there is no point writing the extra term. So I stop here. Okay. So now if I now want to take the L2 norm of this vector, so you can understand that just like v1, v2 up to vn, they were orthogonal unitary vectors. Similarly, u1, u2 up to ur, these are also orthogonal unitary vectors, just like the previous case. So the result which we had got here, the same result I can again apply here. So in the only difference is that this time the coefficients are, instead of being only c1, c2, etc., the coefficients now are c1 sigma 1, c1 sigma 2, c2 sigma 2, etc., and cr sigma r, and so on. These are the coefficients, keeping aside the u1, u2 vectors, which are the which are the new basis vectors. So if I take the L2 norm of this thing, just exactly what had happened in this case, what we are left with is C1 square sigma 1 square plus C2 square sigma 2 square, CR square sigma r square, etc. Okay, so this is what we get. Now we also know that we also remember this relation, that sigma 1 greater than equal to sigma 2 greater than equal to sigma 3 all the way up to greater than equal to sigma r. So the quantity which I have got here can be upper bounded by this quantity, that is that is, since sigma 1 is greater than sigma 2, sigma 1 is greater than sigma 3, sigma 1 is greater than sigma r, etc., we can upper bound this whole thing with with this quantity, right, where sigma 1 is the first principal, I mean the first singular value. Okay, so but what is this equal to? This we have already seen is like it's nothing but the that is, so this L2 norm of x, the squared L2 norm of x is equal to this thing. So now what I am saying is just consider the first r elements of this summation. This summation has n elements, c1 square, c2 square up to cn square. So now here I am considering only the first r of them, like keeping the remaining n minus r aside. But the remaining n minus r terms, they are all positive because they are all squares. So we must write that this thing, this quantity is less than equal to the full summation c1 square plus c2 square plus cr square plus cr plus 1 square all the way up to cn square. But that term again is equal to the L2 norm of x. So here like this becomes equal, so we can get like rather easily that the L2 norm of ax, I mean the squared L2 norm of ax is less than or equal to sigma 1 square times the L2 norm of x. Okay, this should be quite straightforward. So now I can just divide this, and this is the relation I get, that is once you take the square roots on both sides, what we are left with is the L2 norm of x divided by the L2 norm of x is less than or equal to sigma 1, which is the first singular value of a. But this thing is of course like if I take the max of this thing, then what I get is nothing but the operator norm. Okay, so basically it is saying that whatever x I choose, this quantity is less than or equal to sigma 1. If this is true for all x, remember that x is just any n-dimensional vectors. So that means what? That since for any vector x this relation holds, so we can say that the operator norm of a, that also must be less than or equal to sigma 1, just like in this case, just like we had said in this case. So in this case here, note that we had said that the operator norm must be greater than or equal to sigma 1. In this case we are proving that the operator norm must be less than or equal to sigma 1, right? So I have got two results which seem to be contradictory, but there is only one intersection between this. So there is only one way in which both this result as well as this result can hold. And what is that that condition? The condition is of course that the L2, the operator norm of A, the 2 norm of A is equal to sigma 1. That is the first singular value of A, right? So this is a very important result. It's saying that the first singular, that is the, like if I define the 2 norm of the matrix, that 2 norm in this way, the 2 norm of any matrix is equal to its first singular vector. Sorry, the first singular value, or largest singular value. Okay, so this is an important result which will be useful for us in later stages. Now let us come to another result. So let us consider this again any matrix A which is invertible. Okay, so if it is an invertible matrix, it like only square matrices are invertible. We know that. In case of non-square matrices, we have concepts like that's the Moore-Penrose pseudo-inverse and so on. So in fact, we had seen earlier how to derive the left pseudo-inverse of the matrix and so on in terms of SVD only. But let us consider a square matrix which is invertible also and denoted by A. So irrespective of whether the matrix is square or non-square or anything, its singular value decomposition exists. So let us write again A is equal to U sigma V transpose. Now since the matrix is invertible, So I can write its inverse A inverse as the inverse of this product, which is of course equal to V U, sigma inverse U transpose. Why we are able to say this? We are able to say this because U and V are orthonormal matrices. So what's with orthonormal matrices? In case of orthonormal matrices, the inverse is equal to the transpose. Right? We know that U transpose U is equal to 1, just like U inverse U is equal to, sorry, not 1, but I, the identity matrix, and so on. So because these are orthonormal matrices, like I can write the A of inverse is nothing but V sigma inverse U transpose. So here it's like as if we are, instead of transpose, we are taking the inverse. Now if you so it should be, like it should be clear now that the way this has been written, that V is still an unit, like an orthonormal matrix, U is still an orthonormal matrix. That means these V and U continue to serve as the singular vectors of A inverse. Although I have inverted A, but the only but earlier U were the left singular vectors of A and V was the right singular vectors of A. But now it has become that V are the left singular vectors of A inverse and U has become the right singular vectors of A inverse. That's the only change that's the change that has happened, but the V and U continue to be singular vectors. And what happens to singular values? So we can understand that like the singular values, they were earlier, they were the diagonal entries of sigma. Now they have become the diagonal entries of sigma inverse, which is just, and for any diagonal, and this is something which you can understand quite easily, that whenever you have any diagonal matrix sigma, if you take the inverse of it, the only difference is that the diagonal elements get we get the reciprocals of the diagonal elements. The off diagonal elements were initially 0. After taking inverse also they continue to remain 0. So if sigma was a diagonal matrix with the diagonal values as sigma 1, sigma 2 up to sigma n, then sigma inverse is also a diagonal matrix whose diagonal values are just 1 by sigma 1, 1 by sigma 2 up to 1 by sigma n, the reciprocals. Okay. So right, so but remember that sigma 1, sigma 2, like they have a specific order, that is sigma 1 is the largest, sigma 2 is the largest, this is the second largest, sigma 3 is the third largest, and so on, and so they are arranged like this. So now if I am taking the reciprocal, then obviously that order is now going to be reversed. So 1 by sigma 1, 1 by sigma 2, these things will continue to be the singular values of A inverse, but the order is now reversed. So 1 by sigma n is now the largest or the first singular value of A inverse, because sigma n was the smallest singular value of A. So 1 by sigma n is now the largest singular value of A inverse. So accordingly, the corresponding singular vector are going to be un and vn, right? So u1 v1, like u1 was the first singular vector, I mean the first left singular vector of A, v1 was the first right singular vector of A, sigma 1 was the first singular value of A. But in case of A inverse, we see that 1 by sigma n, this is the first singular value of A inverse. Correspondingly, un will have to be the first un will be the first right singular vector of A inverse, and vn will have to be its first left singular vector. Okay, so this is another result to remember. That is, if I can take the or calculate the inverse of any matrix, this is how we get the singular value decomposition of any given matrix. Okay. Now in general, for any given matrix, I can define this quantity called the condition number of the matrix. This condition number is defined like in this way, the 2 norm of A times the 2 norm of its inverse. And as you can understand, the 2 norm of, so that the 2 norm of A was of course its first singular value or its largest singular value, which is sigma 1, and the 2 norm of A inverse will have to be the first singular value or largest singular value of A inverse, which we have just identified to be 1 by sigma n, right? So the condition number of the matrix A is equal to sigma 1 by sigma n, which is equal which is also irrespective of A inverse. We can understand the condition number of the matrix A to be the ratio of its largest and smallest singular values, right? The singular value with the maximum magnitude and the sigma value, the singular value with the minimum magnitude. This thing is called the condition number of the matrix. Now, this like in general, the smaller the that condition number is, we say that the matrix is more well conditioned. And if this condition number becomes high, very high, we tend to say that this matrix is ill conditioned. That is, like if in case of a well conditioned matrix, sigma 1 by sigma n will be quite close to 1, which means that there will not be too much difference between its largest singular value and its smallest singular value. But now if you consider a rank deficient matrix, right? So like there is a matrix A whose rank is R, right? So in that case, like as we have already said that total sigma total n number of singular values are there, but if the matrix rank is R, then only the first R of the singular values are going to be non-zero. The remaining ones, say R plus 1, R plus 2, all the way up to n, are going to be 0. Okay. So now, so clearly, in case of a matrix A, which is rank deficient, the this condition number, which is sigma 1 by sigma n, sigma 1 will of course be the largest singular value, but sigma n will become equal to 0. Right? Because it's rank deficient, that is only up to sigma r are non-zero, sigma r onwards everything, that is sigma r plus 1 onwards, all the singular values become 0. Okay, so then it becomes, this condition number becomes sigma 1 by 0, which of course is strictly speaking undefined. So it basically means that it is we say that this is an extreme case of an ill-conditioned matrix. Okay, so we say in such cases we say that the condition number of the matrix is infinite. So again, this is something to, the condition number is a definition to remember. And also it's important to remember that matrix A is said to be well conditioned if sigma 1 by sigma n is small, that is close to 1. Of course, it cannot be exactly equal to 1, or it cannot be less than 1 certainly, but I mean the least possible value of sigma 1 by sigma n has to be 1, which is the strange case that all the singular values are exactly equal to each other. The other possibility is that it is somewhat close to 1, say 1.1 or 1.2 or even 2, basically some small number which is close to 1, which is slightly greater than 1. In that case, we will say that A is a well conditioned matrix. But on the other hand, as this ratio booms up towards say 1000, 10,000, etc., it becomes the matrix, this matrix becomes ill conditioned. In the extreme case, when the matrix is rank deficient, then it becomes infinity. And so in general, this condition number plays an important role for matrix inversion. So for like in various in algorithms for matrix inversion, which are employed in software such as say MATLAB or R or Python, etc. Like when you are trying to calculate the inverses of very large matrices, you sometimes get a warning saying that the matrix is ill conditioned or something like that. So in case of a well-conditioned matrix, it is straightforward to calculate the inverse. But the more ill-conditioned a matrix is, the calculating its inverse becomes difficult. And of course, the condition number is infinity. That will basically mean that the matrix is rank deficient, in which case, of course, there is no question of calculating the inverse. Okay? That is, the inverse does not even exist. Now so this is basically what we covered is like a few important results and definitions related to the SVD. So just to recapitulate quickly, we defined the 2 norm or the operator norm of the matrix, and we showed that the operator norm of the matrix is equal to its first singular value sigma 1. Then we defined the we understood how, given any invertible matrix A, how to calculate the SVD of its inverse. Then we also defined this conditional number, and we understood how to define the conditional number. Now let us so remember that last Friday we were discussing about low rank approximation of a matrix. In particular, we considered the problem of matrix completion, and we discussed at that time that the matrix completion task in general, of course, is impossible. But if I tell you that the matrix is low rank, then it is possible to complete the hidden values or the unknown values of the matrix. I mean, to a certain up till a certain degree of accuracy. We may not, of course, there may be multiple solutions to the matrix completion problem, but there exist algorithms which will give you solutions that are close enough to the actual solution. Now, so that concept had brought us close to the concept of low rank approximation of the matrix, right? And we had said and we had seen how to define the low rank approximation of any given matrix. So basically, if you are given any matrix A whose rank is R, and you want to approximate it with a matrix whose rank is K, where K is less than R, we had seen how to do that. That is, we simply we consider the singular values and vectors, the first K singular values and vectors of matrix A, and ignore the remaining ones. And using those, you just construct the matrix, the rank deficient matrix or the low rank matrix. In other words, the matrix A, suppose the matrix A has rank R, then it can be written in the following way: summation I equal to 1 through R, sigma I, ui, vi transpose. Now I want to get a rank K approximation of the matrix, and this we had said we can denote it by AK, which is nothing but I equal to 1 through K sigma K, sigma I ui vi transpose, right? This is the what we had called as the rank K approximation of matrix A. So now let us study a bit related to this low rank approximation of any given matrix. So now given any matrix A, so as we had already said that it's suppose the matrix A is full rank, right? So that means what? That means is like sigma 1, sigma 2, all the way up to sigma n, they are all the singular values are strictly positive. They are not, none of them are 0. If any of them were, if beyond a particular point they became 0, then the matrix would be rank deficient. But we are considering a full rank matrix, so all these are positive. Now let's define any quantity epsilon which is greater than, say, sigma r plus 1, sigma r plus 2 up to sigma n. So these singular values, these number, they are all sorted in a particular according to their magnitude. So let us say that sigma is any number that has been I mean this epsilon is any number, any value that has been given to you. So what you do is basically you partition these singular values. So partition them to be greater than sigma and less than greater than epsilon and less than epsilon. Okay. So let us say that these R, in this case R does not mean the rank. R simply means those singular values or the number of singular values whose magnitude is greater than sigma. Okay. The magnitudes of the remaining singular values is less than sigma. Okay. Now, so remember that we had already studied one property, that the Frobenius norm of any given matrix is equal to or the squared Frobenius norm of any given matrix is nothing but the squared L2 norm of its singular values. Okay, this is a result which we had seen last week itself. Now this result we are now like we are going to use a somewhat like just an analogous version of this thing. So if you consider any orthogonal matrix Q1, then Q1 times then Q1 into A, the Frobenius norm or the squared Frobenius norm of Q1A is equal to the Frobenius norm of A itself if Q1 is orthogonal. And on the similarly, if Q2 is another orthogonal matrix, I mean Q1 and Q2 are both orthogonal matrix, then squared Frobenius norm of Q1A Q2, this is equal to nothing but the Frobenius norm of A itself. Okay. So this again you can work out. I will leave this to you as an exercise to prove that this is the case. And this and just to remember that the squared Frobenius norm of A is nothing but the sum of its singular values, right? So that means given any two orthogonal matrices Q1 and Q2, then the squared Frobenius norm of Q1A Q2 is equal to the sum of the squares of its singular values. This so remember this, we will at some stage we will come back to this result. Now now let us come back to this quantity epsilon, and remember that what is epsilon? Epsilon is a number which divides the singular values into two parts. The first R are greater than epsilon, the remaining ones are less than epsilon. Okay. Now the claim is that whatever your matrix A is, now suppose you are given a matrix A like this, which is M cross N, and also let us define the rank of that matrix, the rank of matrix A to be, let us say R. Okay, so A is the matrix A. So please don't confuse these R and that R. So let us say that instead of considering these R is not really the rank of the matrix, but we can call it as the numerical rank of the matrix, that is with respect to this epsilon. That is to say, it basically means that the singular values which are lesser than this epsilon, this value of epsilon, these values, they can be neglected. I mean, they are small enough to be considered as zero. So in that case, we can say that the numerical rank of this matrix is equal to R. Okay. Now don't confuse this numerical rank with the actual rank R. Forget that numerical rank as of now. We will use it later. So let us consider any matrix A whose rank is R. So since its rank is R, it can be written in this particular way. That is sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose, etc. up to sigma R U R V R transpose. Okay. And also let us assume that any epsilon, any positive number epsilon is given to us. Just like in the previous case, some tolerance value epsilon, which may be a small value, has been given to us. Now there exists a claim. The claim is that, or the theorem which is that there exists a full rank matrix A, which I denote as A epsilon, such that the difference, like the 2 norm of the difference between A and A epsilon is less than epsilon. So what does consider, forget the proof of this claim so far. So what are we saying? We are saying that A is a rank deficient matrix R. Okay, and now what we are saying here is that there exists a full rank matrix which is close enough to that rank deficient matrix. So contrast this result with what we had said here. What we are saying here is that consider any matrix of rank R. I can approximate it by a rank K by another rank K matrix where K is less than R. Right? K is less than R. So and further we like last week we had also stated one more result without proof, that if that is, it can be proven that A minus AK Frobenius norm is less than equal to A minus B Frobenius norm, where rank B is equal to K. That means what? That basically means that whenever you have any matrix A of rank R, you can approximate it with a low rank matrix. Further, that low rank matrix can be calculated. I mean that that low rank matrix can be defined in this way. So here we are talking about that is, so the original matrix A, its rank was R. The approximated matrix was AK, whose rank is K, where R is greater than K. So here we are basically looking for a low rank approximation of any given matrix. Now here we are talking about the opposite thing. We are talking about the high rank or full rank approximation of any given matrix. Here we are saying that A is a rank deficient matrix. Its rank is R. Now the claim is that there exists a full rank matrix whose I mean, by full rank matrix I mean that its rank is like as high as it can. So if it is an M cross N matrix, if A is M cross N matrix, then what's the highest its rank can be? The highest of its rank can be is the minimum value of M and N. I mean, if it has M columns and N rows, then whichever is smaller, then the maximum achievable maximum rank this matrix A can achieve is the minimum value of M comma N. So so if we assume that M is greater than N, that means it's a long and thin matrix, then the maximum rank is N. On the other hand, for short and fat matrices like this, where N is greater than M, the rank can be at most M. So when I am saying full rank matrix, that is what I mean. That is the minimum value of M comma N. That is the rank of this of this thing. So what the claim here is that given any rank deficient matrix, I can approximate it to up to any degree possible, or I mean up to any tolerance value possible by a full rank matrix. And the approximation here is to be done in terms of this matrix A2 norm or the operator norm. Okay. So now coming to the proof of this theory of this claim, we say that we define A in the the approximated full rank matrix. Sorry, the full rank matrix we define in the following way. So we continue to use the same matrix A, that I mean the singular values and singular vectors of the same matrix, of the same original matrix A, and then for the remaining values of it, say of ur plus 1, vr plus 1, ur plus 2, vr plus 2, etc., we just use, we just put in these singular vector, these imaginary singular values of epsilon by 2, epsilon by 3, etc. So although this matrix A, its rank deficient means that sigma r plus 1, sigma r plus 2, sigma r plus 3 up to sigma p, all those rank, those sigma, I mean up to sigma n, all those values are of course equal to 0. Right. However, that does not mean that ur plus 1, vr plus 1, or I mean at least vr plus 1, or ur plus 1, vr plus 1, ur plus 2, vr plus 2. These things, however, still exist. It's although they like we cannot define them in terms of the singular values, but we can actually they exist because these v1, v2 up to vr, they are basically forming a basis for, or I mean they are basically linearly independent vectors which are n dimensional. So I can always extend these bases v1, v2 up to vr. I can always extend these to get more linearly independent vectors which will span the entire n dimensional space. Similarly, u1, u2 up to ur, these have been defined with respect to the singular values, but they are orthogonal, like orthogonal vectors which are m dimensional. So I can always extend these bases to get more values, like I mean more vectors ur plus 1, ur plus 2, etc., up to which will span the entire m dimensional vector. So ur plus 1, vr plus 1, ur plus 2, vr plus 2, these we can still get. And so we will construct a epsilon in the following way. So here we just use the same singular values and singular vectors as the original matrix A, and in addition we bring in these kinds of terms. So these so it's like we are creating a epsilon who as a matrix whose singular values are sigma 1 up to sigma r. After that there are subsequent singular values like this sigma by 2, sigma sorry epsilon by 2, epsilon by 3, etc. So these all the way up to epsilon by p, where p is the maximum possible rank of this thing. Okay. So as you can understand, all these, so these are artificially created singular values. They do not actually exist, but I have put them in. The ur plus 1, vr plus 1, these things I have got from A. I mean, I had got ur, vr from A. Then those bases I have just expanded to get ur plus 1, ur plus 2, vr plus 1, vr plus 2, etc. And I have forcibly put in these constants in terms of the tolerance value that was given, the epsilon, to make it as a full rank matrix. So now following this and remembering that the operator, so now if I am looking if I consider the operator norm of A minus A epsilon, A is the original matrix and epsilon is the matrix that we have constructed. So that is the operator norm of A minus A epsilon is by definition of, I mean by the result we had proved earlier, is of course going to be the first, the operator norm of any matrix is the first singular or the largest singular value of that matrix. But remember that A epsilon has been defined in this way, where this part is A itself, right? So A minus A epsilon is nothing but this part that we artificially created. And so clearly this part, these terms, they define a matrix whose singular vectors are ur plus 1, ur plus 2 up to up. These are its left singular vectors. Its right singular vectors are vr plus 1, vr plus 2 up to vp. And its singular values are whatever we have forcibly put along the diagonal, namely epsilon by 2, epsilon by 3, etc., etc. Right. So clearly the large, so since epsilon by 2 is clearly the largest singular value in this case, So we can we understand that the epsilon by 2 in this case, the operator norm in this case is nothing but epsilon by 2, which is of course lesser than epsilon, right? So that means what? That means whenever we are given a rank deficient matrix like this A, I can always approximate it by a full rank matrix A epsilon such that that approximation, I mean that error of approximation is within a threshold epsilon that has been given to you. Okay, so this is like this in a sense is the contrary, like is a contrast to the result which we have claimed earlier, this which is basically this result by Eckert and Young. This result is saying that any like any full rank matrix or any high rank matrix can be approximated by a low rank matrix. So this is what we had discussed earlier, and this the result which we discussed right now is in a sense it's the converse of that. It's like saying every low rank matrix can be like approximated by any full rank matrix. Okay, so so that means what? That means there are like these that is rank of a that is the, it basically means that the if you consider this the space spanned by all matrices, the it's not that the low rank matrices and the full rank matrices are scattered far away from each other. It's not that there are the all the in the space of matrices, it's not that all the low rank matrices are sitting in one corner and all the high rank matrices are sitting in another corner. It's that the low rank matrices and the high rank matrices are very much interspersed. So if you like imagine a space of the m cross n matrices like this, I mean of course such a space cannot be visualized in 2-dimension, but still just if you think. So let us say that if these points like these point if they these points represent low dimensional low rank matrices, we can also find some high rank matrices in their immediate surroundings. On the contrary, if you consider any high rank in any of these high rank matrices, then also you can find a low rank matrix in its surrounding. So it is not the case that there is a separation like this, that is the high rank matrices are sitting in one corner of the space and the low rank matrices are sitting in the other corner of the space. It's like they are all together. Wherever you find a low rank matrix, you will find a high rank matrix also nearby. Wherever you find a high rank matrix, you will find a low rank matrix also nearby. Okay, so that's the that's an insight for linear algebra. Okay. So we will stop the class here, and tomorrow we will see some further properties of these singular value decomposition. Thank you.